Second video here is about drawing graphs and hand drawing a trend line and then finding the slope of that trend line. These are things you've certainly done before in math, but there's probably a couple little details that might be different from what you've done in math, and maybe just a couple things to think about. There's going to be a quiz about this tomorrow, or you might be looking at this as review if you had difficulty with the quiz. Either way, just going to try to give you a quick little rundown on how to draw a perfect graph and trend line. So I've got some data here. It's got time listed in one column and depth listed in the other column. You notice that time is measured in seconds. I know it's a little bit hard to see on the screen. And depth is measured in meters. Those are labeled. So what we've got happening is some sort of container of water. And over time, the depth of that container is going down. Obviously, water is spilling out somehow. First question is actually which of these variables that we're graphing is the independent variable and which is the dependent variable. Remember, the independent variable is what you, the experimenter, would have control over, and the dependent variable is affected by that. So if you have a hole in the side of a container, what you have control over is the amount of time that that water has been flowing out. And then depth is a result of time. It doesn't go the other way. You might be able to change the depth of the water, but that doesn't determine the time. All right, so causation starts with this. This is the cause. This is the effect. In other words, this is the independent variable, and this is the dependent variable. Okay, just a basic rule of thumb that we need to remember when drawing graphs. The independent variable goes on the x-axis. And it's not really the kind of thing where there's a reason for that. We just sort of decided that this is how we're going to draw graphs. And now, if you draw a graph that's not like that, it ends up looking really weird to people who are used to looking at graphs that are all the same. So independent variable is going to be here. We're actually going to include this label every time. So I want you to tell me what is the quantity you're measuring and what is your unit every single time. So we do time measured in seconds. That's kind of the standard way of labeling an axis. You will always lose points if you don't label your axis. On the y-axis, we're going to write depth measured in meters, okay? The next step is to figure out how to scale the axis. What do I actually write down here? In order to do that, we want to look at the minimum and the maximum values. So for time, we have a minimum value of 0. We have a maximum value of 8. For depth, we have a minimum of 1.7 and a maximum of 4. So I need to scale it so that those fit in there. And I want to have several different markers down here that space out the data really nicely. We don't want the data really crammed together because it makes the graph really hard to see. Another big mistake that people will make sometimes is they will simply grab those numbers and put them right here. So they might go, okay, 0, 2, 4, 6, 8, and then they go over there to depth and they go 4, 3.3, 2.8, 2.3, 1.7. I kid you not. I see that a lot. Or they'll do 1.7, 2.3, 2.8, 3.3, 4. You cannot just write the numbers of the data. You have to write a consistently spaced scale. So for time, I'm starting at 0, going to 8. That's pretty easy. I could go by 2s. I'm going to go by 1s in this case, just to space that data out. I have enough room to do it. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. For the y-axis, I'm starting at 1.7 going up to 4. I always like to have 0 on the axis if possible. If you don't go all the way to 0, you end up kind of distorting the data, and especially your trend line ends up looking pretty difficult, pretty weird, and it can make it hard to understand what you're looking at, and it can also make you trick yourself about what you've discovered. So always going down to 0 is a good idea. Sometimes it's not possible. I'm going to go from 0 up to 4. I'm going to go by 0.2. So this first little line right here is going to be 0.2, but I'm actually not going to write it just to save space. So this is going to be 0.4, 0.8, 1.2. Now that my scale is written down there, it's time for me to go ahead and plot the points. So I'm simply going to look at the number for the x, in this case 0, and the number for the y, in that case 4. Just go over here to 0 for the x, and 4 for the y. Go ahead and plot a nice clear point. And keep going from there. Now that I have all of my points plotted, I have what looks like a really nice straight line here. I'm now going to go ahead and draw a trend line. Really important point here, we are not connecting dots. So my trend line will not touch all of those data points, not for real data at least. And so we need to figure out how to draw a straight line that goes as close to representing all that data as possible. We're trying to kind of ignore the little variations in our data. We're trying to get the overall pattern as accurately as possible. And a really good way to think about this is you're going to draw a line with as many points above the line as it has below the line. So if I have 5 points like I do here, the line is probably going to hit one of them or come close to hitting one of them. And it's probably going to have 2 of them below the line and 1 of them above the line. So I'm going to take my meter stick here, and I'm going to try to line it up pretty much over these. So it looks like if I do it like this, I'm going to probably hit that point right there. This one is going to be over the line a little bit. This one will be over the line a little bit. And then I have 2 that are below the line, and that kind of meets my criteria for a good trend line. Okay, notice not all of the points are hitting the line. Another thing to notice is that I do have 2 points clearly below the line. I've got this one is a little bit above the line. This one's basically on the line. This one is maybe just a little bit above the line, but they're going to be very close. So the last step is for me to find the slope of this line. And this is where a lot of people start to have some difficulties because of differences between a science class and a math class. So in math class, you usually have perfect data. Not always, but usually. And so this would form a perfect straight line. In science, we're collecting this data. It's real, and so it's going to have imperfections in it. And so I'm not going to select actual data points in order to find my slope. For example, I would not do this point and this point as my points for finding slope. Remember that to find slope, you need 2 points, and you're going to look at the rise over the run between those 2 points. So I wouldn't pick those. I also wouldn't pick necessarily this data point and this data point or that data point, because like we said, this is slightly above the line. This is slightly above the line, and I don't want the numbers for a line slightly above the line. I want to know the slope of the line itself. So what I have to do is I have to look for places where the grid lines, because usually I'm doing this on graph paper, where the grid lines intersect with the line itself. So I'm going to go ahead and add some grid lines right now, and we'll see if we can find that. So now I have some grid lines drawn on there, and no, they're not perfect. Like I said, we would want to do this on graph paper or something like that. But what we want to look for is a place where this black trend line is intersecting with 2 corners, a place where grid lines actually intersect I know some of the junior high school teachers call them crispy corners, places where the trend line perfectly hits the grid line. And so I see that right here, the trend line and that grid seem to intersect. And I'm going to go ahead and circle that as a place that I'm going to use for my slope. Notice, I'm not circling this black data point. I'm circling that intersection right there. Another place that I see looks pretty good is right here. The line seems to intersect with that 4 depth and 0 time. Now that I have those 2 points, I can go ahead and think about rise over run. So my rise and my run, usually represented by a triangle, can be calculated pretty easily. This value right here is 2.8. This is 4. So the difference there is going to be 1.2, okay, for the rise. Technically, it's actually negative 1.2 because we're losing that much height. The run is going to be 4 because we're going 1, 2, 3, 4. We can actually count the lines here because each grid line represents 1. We cannot just count the grid lines here because they do not each represent a single unit. Another thing to mention is the unit of this. So this is negative 1.2. The unit is meters because it is a y-axis value. That's a big thing that they don't necessarily talk about in math class because they don't necessarily have units on the axis all the time. But when we're talking about real data in science class, these numbers mean something. The 4 means a number of seconds because that is an x-axis value. Okay, so we take this rise and this run, and we do rise over run. So it's going to be negative 1.2 meters divided by 4 seconds. Plug that into a calculator, and the answer is going to be 0.3. Sorry, my mistake. Negative 0.3 meters. Notice meters is the y value over seconds. Okay, notice I got the unit by taking this unit and dividing it by that unit, just like I divided this number by this number. Okay, so our slope for this is negative 0.3 meters per second. Just to repeat this one more time, we are not looking at the actual dots, the actual data points. We are looking at places where the black trend line intersects with the grid lines of the graph. That is a little bit tricky. I will give you a much better way to do that by using a computer to do it for you. But you do need to know how to do it by hand as well.